Okay, so welcome everyone. So it's a pleasure to introduce you to Cristóbal Bertoglio from the University of Groningen in the Netherlands. Cristóbal he's originally from Chile. He did his PhD with Frédéric Jarbeau in INRIA in 2012. After some postdoctoral experience in Munich and even in Chile, he got a position in 2017 at the University of Groningen, where he now leads a group on inverse analysis, cardiac modeling, and fluid fracture interaction. And he, for example, has an ERC project that is dedicated to that topic. So, well, very much looking for, thank you for being here, Cristóbal. Very much looking forward to hear your presentation.
Well, thank you very much, and thanks for hosting. It's a pleasure really to give this talk here. It's my first time at the UPC and at CIMNE. So I'm visiting a conference on magnetic resonance imaging in Barcelona, and I thought that it would be interesting to stop by and see what you're doing and share our results. And then after I can present the talk for the conference, just by compressing this one a bit. So I have a lot of slides. I don't know if I will have time to present everything, so just we will see, and it's okay for me to stop. And if someone is interested in more things, then we can talk later or another time. So not everything, but some of the things I will present today, they are in a review paper. So if you're interested in the topic of inverse problems and imaging and flows and so on, you can. I will strongly recommend to take a look at the review paper. It's already like a bit old, but there's not much new after that. So it's from 2022, and it has around 200 references. So it's, we made a lot of effort for explaining actually what every paper did and what are the differences, and then what are the challenges and opportunities. So that's a good starting point. Okay, so what we do as a research group in a nutshell, so that to put into context the talk, is well, one of the aspects we work on, sometimes more, sometimes less, sometimes nothing, is on numerical methods for fluid mechanics and fluid-solid interaction, particularly focus on rock flows. Now, since some time in the heart, of course, the equation that doesn't fully match the video because I'm not, it's not an AVE, it's not a moving domain form. But especially considering methods for coupling models of different scales, COD, 3D, and things like that. Yeah, well, so, and then a completely different topic, you would say what it is. It's magnetic resonance imaging. In particular, we started to work more in that acquisition and personal post-processing. So if you get already the image as it is, how you, for example, can recover pressure information from velocity data. Then we slightly move to acquisition. So how can you acquire things in a way that then the results are better? For example, encoding velocities in a different way, combining them. I will show something like that later. And then now we're moving towards reconstruction. So really working with the raw data that the scanners output and really see what are the opportunities and challenges. There I also present the results. And of course, well, not of course, but why we do two things at the same time, because we want to combine them. I think there is a kind of, it's possible to set it up. So there, it's fine there, but it's not fine in the screen, maybe.
Actually, this is the screen.
It's possible to.
Ya, pero ¿por qué queda reducido? ¿Verdad? Por la resolución del.
Well, it is not a big problem, but just we can leave it like that.
Igual voy a buscar Windows, señor. Go ahead, go ahead.
Okay. So what we do the combination of the two. So we assimilate, we merge the model with the data, and it can be models of different complexities and data of different complexity. And as a result, we get personalized models, but also we aim with that to create clinical value. So I'm not going to show the clinical work today, but we do that, and we do really data simulation for clinics at the moment, for clinical research still dealing with hospitals and everything that comes with it. So okay, so just in a, so I'm assuming you all work with models with numerical methods. So now some of you may do data simulation or inverse problems. Some of you may not directly, but so just to put it into context. So we have two ingredients. So we have a generic model that could be like PD based, which has some uncertain parameters, either constitutive parameters or boundary conditions. Then we have data. In the case of flows, we could say, well, we have some kind of, no, I'm not. Oh, no, I can't. That's not mine. Okay. Okay, so we have medical, an anatomical image, some information about the image, and we have flow, information from the flow, not the full flow necessarily, but some information. In this case, we have a plane where we have the component of the velocity parallel to the plane. And then by merging the two, doing, for example, some parameter estimation, not only, but you can also statistic, but let's restrict ourselves to parameter estimation, you can expand this information and you create a full 3D model of the. So we will talk about many ways how to do this, and depending on the type of data you have and the model, and we'll see what other technical and mathematical and computational challenges playing in this field, basically. So, and the big picture is, as you can, well, you can intuitively assume, is that the more effort you put into measuring, the less is the effort you have to put in processing. So, for instance, if you have full measurement of 3D measurement of the flow in space and time, up to a certain resolution, of course, it's very easy to extract of it. Easy to extract the pressure field. Basically, you solve one part of the Navier-Stokes problem, you can solve just for the pressure. And also, you can, of course, if you have more data, you are going to minimize a certain cost function. It's more complex. You can optimize also more parameters, so it gets easier. But the less data you have, for example, in this case, only the flow information in some planes, the more challenging becomes the information. Actually, if you go later in the presentation, I will move more towards the right, which is the topic of the ERC project. So the good thing to moving in this direction, that is easier to get data. So the more you measure, it's more difficult to get the data from the hospitals because they don't measure, because they don't have, it's not clinically available. Of course, in the clinic, they have for the flow data, and there is a group of clinical workers for the flow data that I'm aware of it. So it's becoming more and more common. Though they use contrast media, they have GE scanners, so they use contrast media. They cannot use it without contrast media. And but this type of images, you get it in every hospital in the world. Okay. With raw data, in principle, it's there. You only need to know how to extract it from the scanner. It will be always there. So okay. So the inverse problem, you have a certain two quantities, a state and a parameter satisfying a model, and they satisfy a model which is basically a mathematical constraint between the two. And the state will be typically in mechanical problems, displacement and velocities, not pressures are not part of the states. Pressure is just an internal variable of the problem. And then you have in the parameters, you have a bound of, for example, constitutive quantities or boundary conditions. And the idea of the forward problem is that you give theta, and then you solve the model somehow, and you compute the state. Okay, and you get the nice videos and then nice videos you're used to. The inverse problem is you obtain some partial information and perturbed information even about X, and you try to recover the theta. You try to go back. So type of data, now getting more into actual images. This is an anatomical image, for example, of the aorta, how this typically look like. And this will be some flow image actually from the same patient, just undersampled. So we remove some parts so that you can actually see somewhere here is the heart, and then you see how the flow is leaving the heart and into it. So just introducing, and how will this forward inverse problem look like? So for example, this is a toy example. So we have an aortic model. I don't know how well you see it from now. I think you see it well. You have a flow model in the aorta with some boundary conditions. The forward problem will be you solve this problem and then you obtain some kind of measurements, generated measurements. In this case, it's the vertical component velocity to the plane. And you see there should be some engraved anatomical image It's actually not the exact mesh we were using the data, but a perturbed one, like you will have in practice. And the inverse problem is the other way around. So you start there and you get fit the parameters that you get them all. Okay. So obviously this looks harder because you have way less information than here. And this is the whole business. So what we do in the group is how actually go towards getting even less information than that. So really pushing the amount of information that you have to measure to the limit, to the one that is actually needed depending on what actually you are trying to answer. So just to show how we do that, to introduce it, so that with some, say, easier examples, present the methodology, I will just work with 3 to 1 examples. If we have later more time, I will move to some FSI, some results in FSI. But the main message today is a bit like to talk about the imaging side and what are the challenges there and how you can cope with that using the data simulation. So because you are experts, even more experts than I am, in solving the forward problem and actually like solving mechanics. So let's start with the basics. So least squares estimation. So the least squares estimation, imagine that your model is linear. So you map from the parameters to the measurements, it's linear. And you add some regularizer in case you were doing some Bayesian. So Bayesian in the sense of that you have a prior. And then, well, usually the solution of problem is like first year students do this actually. So you take the derivative of the cost function, you equal to 0, and then your estimator can be written. So you can write it in many ways, or ways are equivalent because the problem is linear. But you can write it particularly in this way. So you have the estimator. So the value of theta that minimizes this cost function is theta 0. So your initial guess plus a correction. So a correction that is proportional with some matrix K to the difference, to the discrepancy between the measurements and how good was your prior, how well your prior fits the measurement. So imagine your prior just fits perfectly the measurement, then you need not to do any correction. This term is 0, so you already solved the problem. The more far you go from the prior to the you are from the between the prior and the measurements, let's say, the correction is large, the correction will be strong. The important thing, another important thing here is that this matrix K actually doesn't depend on your prior in the linear case. And it has this form, and actually depends only on the weights on the model itself, not on the prime, but on your knowledge of the physics, and has this shape. So you have the prior for the measurement error. You have the prior for the parameters. You have the model. So no information about the data or the value you assign to your theta 0. The problem is that, well, it looks nice, you can solve this in one step, but if your the dimension of your measurements or your parameter is large, then this is a full matrix and you can just go and solve things. So this is the a big challenge, let's say. So this is not what people do for real world applications. I will show you later how. In the dynamic case, you can write an another problem. So you put a sum over time, your operator may vary over time, and you do the same exercise, and you can show that actually you can decompose your estimator in a predictive step. So just propagate this from one time to another using for operator, and a correction step where you correct it using the data. So you have this two-step approach. And this is in the linear case is exact. In the nonlinear case is not exact anymore. In the linear case, and also when you extend this to unknown parameters and unknown state, you have this form for the forward dynamics. So your cost function looks very similar to the one I showed before. Just now we have a prior for the initial condition, and here we have a nonlinear relationship between the parameters and the data. So even in solid mechanics, so if you have basically take a spring, right? So everything is linear. The relation between the stiffness of the spring and the output is not linear. So even in those very simple cases, you already sort to a nonlinear estimation problem. So there are many ways how to deal with that. So how we do it, it's not we didn't invent that or anything, but so use Kalman filtering. So we do this sequentially because it has so many advantages. You don't need to store the solution for all times. And we're based on the uncentered Kalman filters. Basically, you take a sample of the particles, a sample of your solution at every time step. You generate many of them, right? And then you propagate them using the forward operator, and then you combine them, and then you obtain the next estimate. And then you correct both the parameters and the state, constructing some kind of Kalman. Still, here the problem of that this matrix is large is not solved. Okay, so how do you tackle that? Is by okay, that will be important that is seen, but so if you assume that all your uncertainty is in the parameters, so this term is not there. Okay, for example, you assume your perfect knowledge of the initial condition, then you can write all the matrices involved here in a low rank form. Of the size, the rank is the number of parameters, and then you can just propagate that low rank form over time, so you get something that is very tractable. I'm not going to enter. I can give you the reference for that. And here is hidden kind of maybe this is like you can expand it this like full screen. Maybe.
We checked it.
No, you try not.
Here I don't know. ¿Y cómo se creó? ¿Ya onda ocultar?
Oh, we just continue it.
Okay.
Okay, you see here that the number of n will be the number of particles equal 2 times the dimension of the parameter and plus 1 eventually. So this means that actually you grow linearly with the number of parameters, and that's well, that's convenient. And you can also do all this is parallel. So every solution of the forward problem can be done simultaneously. So quite tractable. I do not have to reiterate, so you do only one shot, and that should be fine. So, okay, this is just to give you the context. So basically, over time, you're going to estimate to correct the value of the parameter, though the parameters, the constants, are not varying over time, as we see here. So we have a Navier-Stokes problem on the aorta. So, and then we'll assume we don't know something. So one of the parameters, we don't know the distal resistance to the flow in the outlets. And we are not, we do not know the peak velocity in the inlet. Okay, that's just one scalar. Nothing varies over time. Everything is constant. But when we're going to estimate those, we'll do sequentially as we get data during the cardiac cycle, try to fit that. So again, same thing I showed before. So we use the reference simulation. We generate some measurements, and these are only those measurements in this case. And then we minimize the cost function that has basically the regularizing part. We estimate all those parameters at the same time, and the data are these measured velocities in this plane, and the observation operator is just the interpolation, physical interpolation from the simulation mesh to this plane. It has quite some course with boxes. And this is important because then we're going to later change the observation operator, something more complicated. So far, it's only an interpolation. And then when we run the Kalman filter, we start for all, this is the results for the resistance, the inflow converges very quickly, so it's not that interesting. So we start from the same value for all resistance. They dance a bit over time until they converge to something. And we see here that they converge pretty well to the reference value. So in dash, the dash horizontal lines out, it's the ground truth we want to converge to. Okay, this is a typical well-working example of the Kalman filter. When everything works, it usually looks something like that. But now that's the more interesting part of the story. Before was kind of an introduction. MRI has problems. So all this inverse problem story works nicely when your model is exactly match the data, when your data fulfills some assumptions that your noise is Gaussian distributed, has no other type of artifacts, but in reality, that's not the case. And here we can see this is for the flow of the same problem. I think this is it's artificially generated, but you can looks anyway very good compared with actual for the flow data. And you see first, of course, noise. You will have noise, that obviously, and it's not noise that is distributed independent each node. It's actually all correlated because the actual noise is in frequency space. So we're going to go to that point later. But also you have aliasing. So depending how you tune your parameters, your velocity basically can swap. We'll talk about that also now. So of course, now crash course on MRI. I hope you have. Well, I don't hope you have. I hope you know what this is about, not as a patient, but as a researcher. So you basically enter to the scanner and you are around electromagnetic coils. So this is how it looks like in a scheme. So these coils generate. So if you do a scheme of this, you are in the table and you have 3 axes, and these coils, there are 2 types of coils. So you have the big coil, the green one, which generates the base static magnetic field. So when you enter to the scanner, it's the noise like, I don't know if you have been in a, that's actually the big coil generating that noise, generating the magnetic field from an electric field. And then you have the smaller ones actually apply the extra pulses, which are time dependent, and also do the readings of the signal. So those are, say, very quick and of lower amplitude, and also vary in space and time. So with this, you play only by playing with those, you generate all the type of images that you are that you can create, that MRIs can create very flexible. So then you create the basically the images, right? So I had a, I don't know if I did. No, probably it's not going to be the case because I have the noise. So this is like, and then it's like and stop. Okay, so the B1 is a and the other is the. I have the noise there, but I have to turn it off. Yes. Yeah. Okay. Good. Yeah. If I passed, yeah, the noise was there. Okay. So what does it mean mathematically? So mathematically, you have all these magnetic fields create a magnetization vector. So you become a magnet, a 3D magnet. There are all the quantum physics behind that explain this. But at the end of the day, you become a magnet, and you create a magnetization vector with 3 components. And these 3 components correspond to the ones of the scanner. And the important ones, the most important ones, are the ones that are perpendicular to you. So the XY component. The other, the Z goes in the direction of the static magnetic field. And this B1, so the small gradient, the dynamic gradient, basically makes appear this XY. So before those, you only had the Z component. You just align your spins, align with the main field. So in one direction, some in another direction, you create a net magnetic field. In order to create the signal, you need the B1, and so that these components appear. And since it is a dynamic gradient, this starts precessing. So this is also dynamic, so it depends on time. Basically, you have a vector that does like that. And if you look at the YZ components, you have the YZ components that do like this. Okay? So this is just, okay. Does it make sense? Not that would. So you're lying and this is the plane. So this is the plane. It's processing. Well, so there are equations for this. And the equation are the block equations. And if you write it actually in Eulerian form, so you can write it in Eulerian form in an L form. So what's the people from MRI usually drop that term, okay? But you can actually write them here, including that term. And that's where the velocity of the tissue that you're actually acquiring the image from appears. So this is with some assumptions. You can decompose this is a vector, so you can get an equation for the phase and the magnitude of the vector separately. And under some assumptions, only you get, so you have the one of the components of this external magnetic gradient and the velocity. So it's actually the phase, not only, but the one that is mostly used, the phase of this vector that is that encodes the formation of the velocity. So basically, you measure, so what the MRI does is measuring that magnitude and then somehow recover that velocity. This is for the flow of phase contrast MRI. So for that, you need some kind of spatially varying field. Okay, so this is the math. Okay, it's a complicated transport equation. Eventually, who knows what is the initial conditions? Who knows, how they get a number there? But this is what they do. They assume that the phase, you go an EDP, PDE course book, the classical ones. This show you how to solve by hand the transport equation. So if you assume that the velocity is constant in space and time, you get this. You can assume that the phase, when you apply a certain gradient, the phase is the reference phase, which is basically your initial condition plus your magnetic gradient times a term that is the velocity times something that depends on the gradient and the magnetic properties of your tissue that looks like that. So the problem is that they both are unknown. So you and this background phase are unknown. This one you select in the MRI scanner. So then you need two measurements for different gradients. So you can then combine them and subtract them and get the velocity. So this is why it is called phase contrast, because you need two phase measurements in order to obtain the velocity. Just subtracting phases. If you write this a bit differently, so you get these two, well, the same, but you write these quantities. You get a pi here and the bank. This bank is just the same thing that's rewritten. But the thing is that I use the technician, the scanner you select is the bank, not the gradients. So the problem is that the bank is basically the range where you can actually encode the velocity. So when the bank is smaller than the velocity, then you get aliasing. Okay, so you start seeing drops in the velocity. But okay, why not to take the bank very large, and that solves the problem. So you take it 1 million centimeters per second and solve. The problem is that the larger the bank, the larger the noise in the velocity image, and this can be seen through this formula. So for a fixed SNR in the image, in this case the phase, which is given by voxel size and a lot of parameters, just changing the bank amplifies so you increase the bank, you amplify the noise in the velocity for a fixed SNR in the image. So that's then not possible anymore. So then in our toy problem, this is how we look at how this is. It looks like this in a real image. It's simulated, but it looks the same in a real image. So for a high bank, you see a lot of noise, and you see no aliasing. For a lower bank, you see much less noise, but you see aliasing, right? What should be blue is red, and what should be red is blue. So, and if you want to say, okay, I want to decrease the noise, I want to use this data for estimate parameters, of course, everything blows out, nothing works. It's obvious. So the question is, what can we do? Just tell the doctor, go and give me the only analyze images and try many times until you get that, or handle this. So we decided to handle this. And first we have to understand the problem. So the problem is that actually, when you acquire phases of a vector that is moving, you don't know in which lab the vector is. It's very simple observation. So the actual problem doesn't really just subtract the phases, but also find out how many labs the vector has done. So you don't get a single estimate of the velocity, you get a family of estimates, an infinite one, theoretically. And what usually you do in practice, you assume you have k equals 0. That's what you get from the scanner. But actually, you have infinite possibilities, right? Of course, you can always construct the other ones by just adding 2 pi k. And when the bank is large, actually the k equals 0 is the correct one, because the vector didn't achieve to do more than one lap. When the bank is too low, then there is a wrap, so it assumes that so you assume the vector did already more than one lap. Okay, so that's the problem. So we need more information to write k, and this is how we start to tackle this is by doing simple image processing. So what we did is to combining a high bank image with no or little wraps and a low bank image, and then create a wrap-free image. So we repeated another scan with a different bank, as you can. There are some mathematical properties that hold, and you can actually show that under certain conditions you can reconstruct wrap-free images. So the effective bank of the two images is larger, even if the two images have wraps. Okay, nice. You can do some acquisitions and play with it, but of course this requires even acquiring more. Okay, but okay, it solves the problem if you're only doing image processing. We actually, it's written here. We extend this. We get a theory for multiple banks. So you can have n images and prove things. Make n10 over infinity, and we apply it to magnetic resonance elastography, where you can actually, it's easier to repeat the measurements and see. And you can see that actually the total, see that this dual image has less noise than the others. I don't know if you see it in those, but it's smoother. It does smoother because we smooth it. It's just because of the combination, it's the combined statistics of the two images. So you get better velocity to noise ratio, and you improve and you solve the wraps. So the key to do this is to rewrite this instead of just taking the images and subtract them, to write this as a least squares problem. So of course you can, from high school, we should know that we can get the phase from the inverse arctangent of the ratio of the components. So this is what kind of MRI people do it by default. But actually you can exactly write the same. You obtain the same when you write the problem as a least squares approach, some kind of inverse problem, and you try to minimize this by the phase, and you get exactly the same result. So it is the same. So of course, then it's nice because this allows you to get all the solutions at once. So then you now use the phase model into this problem. So when you work that out, you get that actually the cost function is just 1 minus cosine of the difference between the measured velocity, the one with wraps, and the one you want to find without wraps. This is just simply using trigonometric tricks. But this is very interesting. So it means that 1 minus cosine of something, it's just a cosine shifted. And depending on the bank, the periodicity of these cosines change. The true solution, the one you're looking at, it's always a solution. It's always a minimum. But all the others will change depending on this periodicity, how you choose this bank, right? So the trick is how to find that one and not another one. And this, what the student actually was, when we saw this curve, okay, what if we just add these two curves? And then if we add these two curves, then of course, boop, this becomes a global minimum. And you just find the global minimum. So then it solves the problem. So just by adding these two curves, this is how I actually generated we generated the images I showed you before. Okay, so basically the trick here is like to add multiple frequencies, to combine multiple frequencies. This is what we learned from it. You can do it by measuring more, or you can do it doing like this. So imagine now you want to do data simulation or solve an inverse problem with data that comes from alliance. So I can stay here. So in this case, so you have one bank for the whole image. It means that you have, for every voxel, say the blue, I don't know if you see it here, but you have the blue voxel that is closer, say, to the peak of the, you have a posoil or you have some velocity profile. The blue voxel around the peak and the red voxel around this part. So the true velocity of the red voxel is smaller than the one of the blue voxel, right? Because it's a lower part in the velocity. If you look at this cost function, 1 minus cosine of this, for each voxel independently, they are just shifted because the true solution is just in a different place, but they have the same periodicity because they all were acquired with the same bank at the same time. It's just one image for the whole region. So Okay, so if you just say, okay, now you introduce a relationship between the boxes. You have a model, a geometrical model of the flow, where the velocity at voxel S is theta times some coefficient at the voxel S. The theta is the same for all boxes, and only the coefficient changes. Like you will just reduce order model basically of the flow. So you have one mode, you model all your velocity profile with one mode. You see? So just to do a coordinated estimation. But the good thing is now, instead of when you write the cost function for all the boxes at the same time, you basically in terms of the parameter theta, and not now in terms of the parameter velocity of each voxel. Of course, the bank is the same. So you get a frequency, so a sum of frequencies, which is the bank, so the coefficient of the mode divided by the bank. So you are summing a lot of frequencies. And when you sum a lot of frequencies, you get a picture like that for the whole construction with respect to theta. And it suffices to start close enough to the actual theta to, when you optimize, to land in the real theta. So now you introduce more information, which is not more measurements, but some assumptions on the profile of the flow that we're using. This is just a motivation now. So it means that if we constrain so if we can map the velocities to some parameters in a clever way, then we can actually work eventually with aliased data. And this is what we did. So the nice thing about that is that we take the same inverse problem, so our quadratic cost function we had before. You only need to change a line in the code instead of minimizing when you compute the discrepancy between the measurement and the model. You just put it in a multiply by pi divided by bank, put it in a cosine, and do a 1 minus over it. The only thing you have to change is really one line in the code, or two lines if you're computing a derivative, but the derivative is just a sign. So, and a factor. So it's trivial. You don't have to change anything. And voila, it's kind of a miracle in the sense that this is the Kalman filter run for one of the resistances. So in the standard inverse problem, say without the cosine, the one I showed before, it blows up. You have aliased data. If you can, the green curve is just you try to remove the aliasing artifact independently on the model. So you try to do some post-processing. This is what people do. Of course, things get improved, but you don't come back to the right parameter. And if you just take the pure raw aliased data and you plug it into the data simulation software, the framework, you converge nicely to the parameter. Actually, it even helps because if you increase the length, your data is less noisy. It's less noisy. So even if you keep decreasing the length, it still works even better up to a point that it doesn't work anymore. So because you are too far, so the cost function becomes more and more like this. And if you start from the same initial guess, then you're not landing in the right. Okay. So in some sense, this parameter, it works when the parameter has a spatial influence over the model. So if you change one resistance, and for example, all the flow changes a lot. Right? If it changes only local, then it's probably not going to work that well. Okay, this has to be taken into account. Okay, because we have a time constraint, probably I will present this and not the SSI part, because I think this is the first time I actually present these results, or the results of real data. We remember this picture, the more you measure, the easier it is to solve the inverse problem, right? Even if you get the good bank, then it's even easier. If you get the bad bank, you get a license, you need to work a bit more to tackle that. But the less effort you put into the measurements, let's say, the more complex mathematically it gets. Well, the example before was quite easy, but you need to understand quite a lot to get there. But the more complex it gets. So let's go a step further and not only measure undersampling space, but undersampling frequency. Okay, so with the hope that you can cleverly select which points in the frequency domain to sample, such that you get the model, the estimated parameters of the model you want. So crash course on MRI now at a deeper level. So the image, the magnetization vector is not what actually is measured directly. What is actually measured is the Fourier transform of that. Maybe some of you know this. So basically, you have a brain image. This is what you see in this is the magnitude of the magnetization vector. But actually, you can go back the data that is actually measured is the frequency transform, Fourier transform. And of course, if you sample everything in the frequency domain, then you can go back and forth using just the Fourier transform. The thing is that especially if you're thinking about 3D measurements, there is no way in a reasonable scan time that you actually can sample the full frequency, right? Because it's sampled line by line and it's sampled sequentially. So it takes very long. So actually, the fastest you can get in practice in a scan is usually I equal, even a phantom, a static phantom that doesn't do anything, it cooperates and everything, it's I equal 2. So the acceleration factor 2. So acceleration factor is a factor R, so 1 is full. You measure everything. The larger they are, the less you measure. So, and you can, when you select less, you measure less, you can also decide in which way you're going to sample your frequency space. And there are plenty of options, okay? So these are 3 kind of, say, common options. One is fully Gaussian, so this is a 3D problem. So we're measuring lines in that direction. So this is Gaussian sampling in that direction, just full lines in the other direction. And then you have spiral type of sampling, and you may have a radial type of sampling. You have probably other types of sampling. Also, Cartesian will be just lines like that, but people usually don't do that. And then if you increase the R, so you measure less for each of the samplings, it may look like that. So the same pattern, but just less steps. Okay, I think this is clear. Then when you measure less, then you need some assumptions. So people from MRI, they use some kind of either some compressed sensing type of thing. So they assume some sparsity transform that actually allows you to regularize the problem. There's plenty of things, way how to do it. So this is just some results, like what happens if you do that. For our toy problem, if you just make a cut in the arch, so you have the ascending aorta, in this the ascending, this the descending one. So you have a lower velocity. So for this, the reference, R equal 1. So we created the K-space. We had noise, and then we apply the inverse Fourier. So this will be the best you can get with noise in the K-space. Okay? So already it doesn't look as great, and no artifacts, anything, just purely mathematical tricks, quite clean. And this is how it will happen if you undersample the K-space and you reconstruct it using some kind of compressed sensing algorithms. You can see the result changes a lot from depending on the mask, and also it changes a lot when you increase the acceleration. And this is already quite accelerating. In practice, you don't use those. Some clinical research, some groups are using around that, but usually if you go to the scan and do some acceleration, it's 2, 3, maybe 4. So it's no more than that, because then you see that also the quality of the image deteriorates quite a lot. Okay, so of course, if you use this data in the inverse problem, it's not going to work, right? I probably now at this moment I don't need to convince you much about that. So what we do is the following. So let us make our observation operator. It's another data. So how we can just make our observation operator more complicated? And actually, this is the same data fidelity term that usually people use in compressed sensing. So we have this is the spatial interpolation. From our model, at each time step, we interpolate in space, and then we apply the magnetization model. Okay, we get the magnetization, and then after we get the magnetization, we Fourier transform. Okay, so there are some small things that I'm here. So you have a number of coils that measure, and it's in practice a bit more complicated, but just would be the kind of the simplest case. So this is the Fourier, discrete Fourier transform. This is the anatomic image. So we assume that that's the anatomic image with some errors. Usually this is part of another unknown of the problem. So we are for now keeping them fixed known with some errors, but no, it's not part of the optimization. The background phase that I presented before is also there. We're also assuming it given with some errors for now. And then you have the measurement noise, and here the measurement noise is usually assumed Gaussian in the K-space. So that's the best what people know about noise in MRI. That is Gaussian, additive in K-space. So it's not additive in the image space, it's additive in K-space. Okay. And this, we know that this is, well, the hazard, and as I showed before, has a nicely square structure, and we can solve it using the assembly common filter. And this is the result. So in the left, you have what happens if we estimate, this is for the inflow amplitude. When we reconstruct the data, the velocities, using some, say, image reconstruction, standard image reconstruction. And of course, since when we increase the R, the quality of the reconstruction decreases, we are more far from the ground truth, right? So our Kalman doesn't converge to the ones, it just converges to the accuracy is reduced when I decrease the data, because the quality of the velocity image also lower. But if I use the data estimation on k-space, starting from the same values, we are much better, and actually the sensitivity is also reduced with respect to the so this actually works under certain assumptions that I gave before. It's working very well. This is a purely synthetic data case. So this is the same aorta data set I used for the other examples. If we go to the resistance, one of the resistance estimations, I plot that. The results are, the difference is less, but it's still a bit better in terms of estimation. So the scales are not exactly the same, but here we converge with, say, the blue curve, the red curve here is closer to the red curve here, so this works better. For the other acceleration factors, it's not that far. It's not much more far than with the k-space, but still k-space is a bit better. So it will depend on the parameter you're looking at and the noise visualization, many things. But for example, if you look at the quality of the reconstructed flow, so you take the estimated parameters and you simulate again, and then you compare with your ground truth velocity field. So overall, so if you just do it, this is for BART means here, this is using the image reconstruction before the inverse problem. This is using the inverse problem from the k-space. We see that the error, this is the L2 error of the velocity, is much less for the when you reconstruct from the k-space. Of course, under some assumptions. And also, but you see, there's also, it depends on the type of sampling that you use. And that's important, an important message. And this is the result. The first time we present the results is with real data. This is a carotid phantom data from Amsterdam. And this is actually how the, this is for R equal 2. Okay, so this is highly sampled. This is what an actual for the flow looks like. Yeah, okay. But this is with highly sampled data. And the idea here is, can we estimate, this is a quite simple geometry, can we estimate the peak velocity in the inflow and one outflow resistance in the out? Okay. So we have only two parameters. So it's a quite simple inverse problem, but we see. But this is real data, so we see it works. And actually, if you use this Gaussian undersampling, we see that here we don't have any ground truth. Right? So we don't have any ground truth. But actually, we have kind of from the highly sampled data. So this is just two acceleration factors, 16 and 32. So these are acceleration factors people from right green. Then we see that the inflow velocity estimates converge quite to the same, a similar value when we change the acceleration. This is quite wrong. It works quite nice. The same for the outflow resistance. Okay, this is for the Gaussian undersampling. But if you go to the spiral undersampling, the other one, then story is a bit different. So the inflow velocity is still kind of fine, but you see that there's much more sensitivity in the value that you estimate for one of the parameters. So then this is a Pandora box, because what you actually should do, and what we're starting to do, is to do optimal experimental design of the k-space sampling. So actually, what do we want to estimate in the model, and how do we need to sample the measurement space to reduce the sensitivity of the parameters we estimate, and this will depend on the model, on the parameters. It's completely new research line basically, well, it's quite well known in statistics, and for PDEs there's already a tradition, but only for optimal placement of sensors. For example, you have a mechanical system. but nothing related to complex measurements and frequency measurements and so on. So, okay, I think I probably will finish because the next is about FSI, and I think that's a bit go too long. Thank you very much, and well, you have any questions?
Thank you. Thank you, Cristóbal. Time for the questions.
So a clarification, I didn't understand. So you said that in clinics they use an R of 2 or 3, but when you undersample, you increase the R. So I don't understand, like, why would you want to undersample so much if in clinics they already use like
that's a very, yeah. Okay, why we would like to, that's probably the first thing I should have explained. Thanks for the question. So, because then you can accelerate the scanner. So instead of acquiring 20 minutes or 10 minutes, you can maybe acquire under a minute. And you can measure more.
Yeah.
For instance, if you are able to acquire to only some parts of the case space, so if you have and I think this is very relevant. So usually when you have the, so how it is acquired in cardiovascular is that you have, say, time, and then you have one cardiac cycle, another cardiac cycle, and another cardiac cycle. And then you divide one of the cardiac cycle in your time resolution. Okay, so you have here, I know, 30 milliseconds, and this is 1 second. So how it is acquired? So you are limited to a few numbers of case space, lines of case space, per time window. You acquire a few lines, and then you go to the next, and you acquire a few lines. And then when you move to the next cardiac cycle, you acquire the next. And then here you acquire the next. So what you get actually, when you look at the image, it's just one cardiac cycle. It's actually lines of the case space that were acquired around the same time in subsequent cardiac cycles. Second, if you will be able to acquire, to estimate your parameters of KTM only with this information and not forget about the rest, you can do them real time. So you can acquire, you can do real time modeling and imaging at the same time. And why you would like to do real time modeling? What there may be surgical applications, or this the application we have in mind is exercise imaging. So we like to look at your heart in exercise. And for that, you need to decrease your either decrease your time resolution. So this make more lines here, and also your total cardiac cycle also. Plus, you have more motion artifacts and so on. So you like to do this as soon as possible. So actually, we have a project on exercise imaging and modeling, and but not using this. It's just a standard image that gives you. And the only way to look at the heart in a few slices in exercise is with real-time imaging. And real-time imaging, what they do in real-time imaging is to basically decrease the time resolution. So instead of having 30, you have 50 milliseconds, so that you can acquire more lines in the case space. So and then reconstruct only from that, so that the image doesn't look that bad. Does it make sense? So it's not real, it's real time in the sense that, yeah, you go and you make your time step of the image longer, so that you can get a better image for that time frame, so that you can just go on. You don't need other cardiac cycles to keep filling the case space. But you lose information anyways, because you increase your time resolution. So it means whatever are you measuring here is some kind of combination of effects of different types, and which makes even less sense if you are thinking about exercise, because in exercise your say heart dynamics and heart flow dynamics in a normal without exercise do like that, and so in rest, in exercise they do like that, right? So you should increase your time resolution also. So So real time gives you an illusion you can scan exercise, but it's not an accurate scan of exercise because it increases the time resolution. So I think eventually by using this type of approaches in the long-term future, can be a great tool to do exercise modeling, which can open also plenty of think applications because, well, you work with principle, you know that the response at rest is completely different than the response at exercise. And they want also to do physical stress. So in Groningen also they produce it was just chance. So they produce there's the company that produces the bikes, the ergometers for the scanners. So we are doing also measuring things at exercise. Yeah. Okay, it's a long answer to yours, very short, but it's very relevant question. Yeah.
Yeah, so, well, do you have maybe one short question?
How is the resolution of the machine? For example, we are talking about just playing with the bank. It's possible just for coronaries and all this stuff, or you apply, for example, you want just to obtain the velocity coronaries.
Yeah, good point. Yeah.
This kind of methodology is possible just to acquire real velocities or coronaries?
You mean for the flow?
For the flow.
There is a group, the people we collaborate on in Amsterdam, they do acquire for the flow in velocity in coronaries.
But they are applying this kind of technique?
Not yet. We like to do it. Yeah, we would like to do it. We just submitted a grant.
Yeah, for example, in the case of aortic coarctation, that you have like quite different velocities in the same aorta is high. Yes, the coarctation is quite high.
Yeah.
This kind of technique is possible just to reconstruct properly all the velocity fields.
So they try to acquire is only the main coronary branch and then the left hand one.
No,
I don't know even the anatomy terms, but so the main one plus the other two. That's what they can acquire up to a certain. So after that, it's
this is coronary, but in aortic coarctation.
Yeah.
In aortic coarctation, because we have like one narrowing in the middle of the aorta, and the velocities in that part are quite high.
Yeah.
Compared to the other.
Yeah.
And just as you something that understood correctly, and you can play with different banks in the same image, and you can just reconstruct all the velocity field properly in just
so you can use this as a way to de-alias your image. So usually, if you, in that case, then the stronger the narrowing, the higher you need to take the bank, because otherwise you get aliasing, right?
Yes.
So with this, you could try to actually just keep the bank, and if there is aliasing, the more you estimate the boundary conditions that may remove the aliasing. Yeah. So that's an application indeed. Yeah.
Okay, so well, for the sake of time, maybe we need to finish here, but Cristóbal will be around for some time this afternoon, so if you have questions, maybe. Okay. So thank you very much.